Hello. All right, in today's lecture, I'm going to talk or discuss an example where I'm going to use velocity and acceleration equations in secondary frames. In other words, I'm going to define two frames. One of them is rotating with another frame with respect to initial frame, and then I'm going to use that to solve and find velocity and acceleration for this point B. We have this, let's say, robotic arm. This is an extending arm. This side of the arm is fixed to the reference point, to the origin, and then point B is the distance from point B to this origin will change. The length of this arm would change, it would increase, and we do have the rate at which the length of this arm changes. So we know that dl, this is L, dt, is equal to 0.25 meters per second. So this arm would extend. And as this arm extends, the whole body, the both arms are rotating about j hat axis. So we have this j hat axis and we have omega 2. And omega 2 is 0.3 radians per second. And then we also have omega 3, meaning that as this arm, or as both arms, both lengths, rotate about j hat axis, they also rotate about k hat axis. So this angle theta is increasing. And we know that theta dot is equal to 0.4 radians per second. Theta dot is omega 3, or omega about k hat. So we know that delta dl, the time rate at which L extends or changes or increases, it is 0.25 meters per second. We have omega 2 and we also have omega 3. Note that for all of these numbers, what we're saying is this velocity and this angular velocity and this angular velocity, omega 3, they are all constants. In other words, the omega 2 dot is equal to 0, or omega 3 dot is also equal to 0, and L double dot is also equal to 0. So at fixed rates, they are increasing. So and then what I've done here is I've defined this is my initial frame, and then I'm also defining a body attached frame. Right? I'm defining my body attached frame such that my b hat 1, I'm using b, small b, to indicate unit vectors in body attached frame. So b1 hat is unit vector along this arm, and then we have b2 hat, and then b3 hat is going to be about along k hat. So this is essentially a right-hand rule, right? Because if I define my b1 hat in this way and b2 hat perpendicular to b1 hat, then my b3 hat is got to be along k hat. Well, now I have all these. I have defined my problem. So I have this extending arm. I have angular velocities about omega 2 and omega 3. There is no angular velocity about omega 1. It is equal to 0. And I also know that the length of B changes, not the length, the distance of B with respect to the origin of this arm, or this point of this arm increases. So what I'm going to do is I'm going to say, all right, well, how can describe velocity of B? That's the question, because at the end, what we are interested in is, I'm interested in VB. And when we say BB, and we also interested in AB, acceleration. And when we say VB and AB, we mean inertial velocities and acceleration. So what I'm going to do is, instead of directly going and computing velocity and acceleration of B, what I'm going to define is, we define this body attached frame. So I'm going to say, all right, so we had this equation. We said that R dot is for point B, and which is essentially velocity of point B. I'm going to drop the subscript B just for clarity of notation. I'm going to use only R. So R dot is equal to our circle. We have this equation with respect to our secondary frame, and then omega of the frame, or the body attached frame, cross R. Right? We already had this equation. We just need to pay very close attention on how each one is defined. R dot is what we are looking for, our velocity of point B in inertial frame. Our circle is the velocity of point B with respect to our secondary frame, with respect to our body attached frame. So my body attached frame was B1 hat, B2 hat, and B3 hat, right? This frame, as this body rotates, is attached to the frame. So if I, as an observer, if I attach myself to this body attached frame, what do I see in terms of velocity of B? How does the position of B varies with respect to this body attached frame? So if I attach myself, say I'm attaching myself to this point and I'm watching point B. So because I'm attached to the body, I'm rotating, right? I'm rotating with omega 2 and omega 3 as my angular velocities. So the only thing I see if I attach myself to this point is how the distance of B with respect to myself changes. And the distance of B with respect to me is defined by L. So the rate of change of that is my R circle, right? So I'm going to say R circle is equal to L dot, because when I'm attaching myself to this body attached frame, the only thing I see is how the distance of B changes with respect to me, with respect to myself, and I'm attached to the body attached frame. I don't see rotations, right? Because I'm rotating with the same angular velocity as point B. The only thing I see is, all right, as I'm watching point B, I see how far point B goes. So which is characterized by L dot. And in terms of direction, in body attached frame, L dot is always along B1 hat, right? So this is going to be equal to, we have 0.25 meters per second and B1 hat meters per second. And if I ask you at this instant of time, what is the position of B in body attached frame, you would say, all right, so the position of B in body attached frame is simply L B1 hat, right? And L is also given, L is equal to 6. So L is 6 B1 hat. Again, we are in body attached frame. For both of these parameters, R circle and R, we are describing these two vectors in body attached frame. Now, to compute R dot, we also need omega, right? Omega describes the rotation of the frame, which is attached to the body. And the rotation of the frame, we said that in general, our angular velocity has three components, omega 1, omega 2, and omega 3. in this case, omega 1 is equal to 0. We only have omega 2 and omega 3. So if I were to describe it in vectorial form, or in vector form, I have omega 2 about j plus omega 3 about k hat. Again, to remind you from basic mechanics dynamics, these unit vectors describe the direction about which you rotate. Omega 2 describes rotation about j hat, and omega 3 about k hat. So this is going to be equal to 0.3, this is given, 0.3 j hat plus 0.4 k hat. And this is radians per second. So I have omega, I have r, I have r circle. So then you simply say, alright, I'm going to substitute all these parameters into our equation, general equation describing velocity upon being in inertial frame, r dot. Again, I'm dropping subscript b for clarity of notation. I don't want to carry all this r sub b, r circle sub. So r is describing b. So we said that, alright, we have omega, we have r, we have our circle. Now what should we do? So the question you should ask yourself now is, what should you do with these unit vectors? That's your next step. So now you should understand why we use a secondary frame, because it was pretty easy for us to describe R and R circle in body attached frame, all right, in terms of B1 hat, and then with respect to B1 hat, and then at the end though, when you're supposed to add these two vectors, R circle and omega cross R, or you perform this cross product, before doing that, you would need to describe all your vectors in the same frame. So then we go back and we talk about transformation of frames, right? So at this point, it's going to be basic math, because what we are concerned, or what we need to do, is first to describe B1 hat in terms of I hat, J hat, and K hat, and then perform this operation. Right? So if you look at this figure, my B1 hat and theta is also given, all right? Theta is 30 degrees. So B1 hat is equal to cosine theta I hat plus sine theta j hat. That's pretty straightforward. B1 hat is cosine theta I hat plus sine theta j hat. And theta is given. Theta is 30 degrees. So we can compute this number. Alright, now I have B1 hat in terms of I hat and J hat. All I need to do is to replace B1 hat with this expression and then perform this cross product and compute velocity. Right? So if I do that, so R is going to be equal to 6 cosine theta I hat plus sine theta j hat, and theta was 30, so I'm going to perform this simple operation and get 3 I hat plus 3 j hat meters. And same thing, this was R. Same thing for R dot, R circle. So R circle is equal to 0.25 and cosine theta I hat plus sine theta j hat. Right? And then we simply, again, we have theta, we simplify these terms and get 0.2165 I hat plus 0.125 j hat, and this is my velocity. Now I have everything I need, right? So if I number this equation and I say equation 1, and this is 2, but omega is 2, and this is my 3, and this is 4. So what I'm going to do is use 2, 3, and 4 in 1 to get r dot equal to, all right, I have our circle now, 0.2165 I hat plus 0.125 j hat plus cross omega r. Omega was this 0.3 j hat plus 0.4 k hat cross r 3 I hat plus 3 j hat. Okay, pay attention. This is a cross product. So if you don't remember how you compute cross product, just go back to your basic math 101 and then compute this cross product. Right? So once you perform this operation, you can simply add these two and get, let me add it here, this is equal negative 0.985 I plus 2.2 j minus 1.56 k hat, and this is meters per second. All right, so we have our circle and we have computed r dot, and this is what we are looking for at the beginning. So r dot is the velocity of point B. Again, just to remind you, this is r dot, velocity of point B. So now that we have the velocity of point B, our next lesson would be about the acceleration of point B. All right. Thanks for paying attention.